For this video, we are going to look at the region between curves. This was touched upon at the end of Calc 1, and it's a very nice extension of integration. Essentially, what we are looking at is if you have, suppose we got a curve here, and we have another curve here, right? So we'll call this one f of x and g of x. So one of the things I want to review very briefly is what actual integration is when we talk about Riemann sums in the area. When you integrate, if you recall, what we're really doing is taking infinitely many rectangles to determine that area between A and B. So if we're going to do an area, let's, I don't know, let's put A over here and B here, right? So we want the area between these two curves. Essentially, what we're creating is infinitely many rectangles, right? We called them in Calc 1 Riemann sums. Infinitely many rectangles between these two curves. So if you think of that area, when we talked about in the Riemann sums, it was essentially to get an area of an individual rectangle. Well, think about it. Wouldn't you just take basically your f of x sub, I don't know, we'll call this one here x sub k for this one rectangle right here. We're going to take one rectangle, x sub k, minus g of x sub k, right? And that, taking this value here, whatever f of x is at x sub k, subtracting g of x sub k, will give you the height of your rectangle. And if you simply multiply that height by the width of the rectangle, if you recall from Calc 1, we called those widths the change in x. You could sum all those rectangles, where your k, you have anywhere from 1 to n k's. We did examples in Calc 1 where we just let n be 4 and you calculated the area of those 4 rectangles to estimate an area under a curve. But then we also learned, well, wait a minute, instead of estimating it, if I then take the limit as n approaches infinity, I will then be able to use infinitely many areas, infinitely many rectangles between A and B. Then we learned that anytime you take a limit of a summation, essentially what we are doing is taking an integral from our lower limit to our upper limit. And this integral is going to end up being, because we're looking now at the area between two curves. So essentially when we did it, the area, suppose, forget about g of x for a minute. Just look for a second at our f of x function. When we were looking at the area of f of x, you were still looking at the area between two curves. It just so happened that whatever this was the curve y equals 0, which is your x-axis. When we went to the x-axis, y is 0, so we never did minus 0. That just wouldn't make sense. So we didn't have to worry about that. But now that we are going to add in this curve, we're no longer going to the x-axis, which means we're no longer subtracting 0. We're subtracting our g of x function. So it's f of x minus g of x dx. But theoretically, you are taking the area of infinitely many rectangles that are formed between f of x and g of x from a to b. And that, as you recall, is what an integral is. So now, to do an example, let's do a little trig review as well. And I want to find the area between two functions. We'll do trig, but we'll keep it kind of simple. Y equals sine x and y equals negative cosine x. Now, obviously, these are two cyclic functions, so there's going to be infinitely many areas. We're going to limit it to one part of these functions. So the best thing to do first, of course, is to sketch your functions. So let's do a quick little sketch of sine of x and cosine of x. Sine of x, of course, it's going to go through the origin, come back around, and it looks something like that, right? Now, negative cosine x. We all know what cosine x. Cosine x starts at 1 and kind of loops this way, right? But we don't want that. Let's erase those dots. We need to start down here at negative 1. And it's going to go something like this, okay? So we're only looking at one period of these functions, and essentially we're going to use the period that the origin is in, and I want this area. There we go. So this function here is our sine x, and down here. And that's important because when you are finding the difference between these areas, you always want to start with the upper function minus the lower function. That is important. Now, oh, that's not bad, so bad. So we're going to do the integral of sine x minus negative cosine x dx. Well, I need to know my a and b, right? So normally, there's my a, there's my b. Normally, we can just set these two functions equal to each other because they're both equal to x. So you end up with sine x equals the opposite of cosine x. That really doesn't help us. Helps us great when we're working with polynomials. Does not help us when we're necessarily working with trig functions. So you have a couple options here. One, of course, is to get it into Desmos. And if you're working on a lab, I strongly encourage you to use Desmos. If you're working on your own in MATLAB, I strongly encourage you to use Desmos. And any other GeoGebra is another great online tool for graphing. But what if I gave this to you on a test, right? You have to think through it a little bit. So think about it. What is the only angle where the sine and cosine function even have the same value? And if you recall, that always occurs at pi over 4, or in reference to the unit circle, anywhere where you end up with a right triangle that is also isosceles, meaning the two legs are exactly the same. So that is how you will get values, and they are the square root of 2 over 2, where you will get your sine and cosine values the same. But to get them the opposite, now you got to pick quadrants where the angles are the opposite. So in quadrant 1, they're both positive. That doesn't work. In quadrant 2, they are the opposite. So that would work. Quadrant 3, they're both negative. That's not going to work. But in quadrant 4, they are opposite. So that would work. So then what are we looking at? We're looking at these two quadrants. And if you relate it to your graph, you can see, okay, in quadrant 4 here, that means this value must be negative pi over 4. This value is clearly past 90. 90 is here. That would be pi over 2, of course, if you know your sine graph. And it's going to end up being pi minus pi over 4, and that's going to end up being 3 pi over 4. So having a good understanding of your unit circle, having a good understanding of your basic trig functions and your trig ratios for angles such as pi over 4, pi over 3, pi over 6, your quadrant angles is really going to help you. And it allowed me to just say, hey, I know this is between negative pi over 4 and 3 pi over 4, of course. If not, what the other thing you can do, get into Desmos, graph it. Here's our graphs of our two functions. I have sine x, I have sine x is in red, negative cosine x is in blue. And then use your cursor to kind of come here. Of course, I would need to be, which I appear not to be, in. Don't forget to switch your settings to radians, and which I was in a minute ago. And you can step, if you put your x-axis between pi, right? Well, let's make that, hold on. You don't forget to play with it. Put it between negative pi and pi with a step of, I don't know, pi over 8 or something like that. That will ensure that when you use your cursor, there we go. We have 3 pi over 4. And then when you come here, you have, yeah, it doesn't want to do it over here. But you can see it's occurring at negative pi over 4. There it is, negative pi over 4. So please, it's a lot of the things we're going to do in this course, you getting very familiar with Desmos and knowing how to use it and help you to get things graphed is going to be pretty valuable. All right, so now I know that my integral goes from negative pi over 4 to 3 pi over 4. All right, so we're going to clean this up a little bit. And I'm going to move it down. And we are going to integrate from negative pi over 4 to 3 pi over 4 of sine x minus minus, of course, is plus cosine x dx. Always put this in parentheses. And you can hit pause and try this integration on your own. I kind of suggest that. And then when you come back, you will see it completed. So of course, when we integrate, we are going to end up with negative cosine x plus sine x from negative pi over 4 to 3 pi over 4. We have already determined that these are all various negative or positive answers of pi over square root of 2 over 2. That's what cosine and sine of a pi over 4 or a 45-degree angle is. So you just have to think quadrants for a minute. So we're going the opposite. The cosine of 3 pi over 4, 3 pi over 4 was in quadrant 2. Cosine was negative. But the cosine of a negative, and then the opposite of that, is going to end up being a positive square root of 2 over 2. Now, sine of 3 pi over 4, of course, that's in quadrant 2, where sine is always positive, so that's just positive square root of 2 over 2. Then we're going to subtract. Now we're going to use negative pi over 4. Negative pi over 4 is in quadrant 4, where cosine is positive. All right? So cosine of negative pi over 4 is positive square root of 2 over 2, but there's a negative out front, so we end up writing negative square root of 2 over 2. Negative, again, is in quadrant 4. Sine is negative in quadrant 4, so it's negative square root of 2 over 2. And if you distribute, we end up with 4 square root of 2 over 2, which equals 2 square root of 2, which is the area between these two functions. So again, this will work the same way for any two functions. Now, let me throw in something a little different. Suppose we had so let's do y equals x squared as one function, right? Y equals 4x. My ratio, they're going to be off a little bit. That's okay. This is y equals 4x. And let's do y equals 4. I just want to fix up my picture for that. There you go. Fixed up my picture a little bit. So we have the part of the parabola, y equals x squared. We have the line, y equals 4x, and then we also have y equals 4. And what I want is the region that is bound by these one curve and two lines. Now, keep in mind, let's go back to our Riemann sums. We have to be able to draw these rectangles between. Right? So if I want to get this area, I got rectangle, all these rectangles, and I'm good till here. Because up to this point, right, I can take the function 4x minus x squared. I'd have to figure out that point, but that's pretty easy to figure out. 4x, oh, that's just going to be y equals 4x and y equals 4. That's just going to be 1. Sorry, not wrong one. And that's going to go from 0 to 1. Problem is, I cannot use that for the rest. So in green, we've got this other set of rectangles. Now for that set of rectangles, I would have to use the integral from 1, well, to here. So that's clearly a 2. But now I have to do 4 minus x squared dx, and I have to add these two areas together. Not horrible, right? Not horrible. It can certainly be done. You can easily integrate both of them. You've got two integrals, polynomial integrals, just using the power rule. Integrate, evaluate from 0 to 1, evaluate. If you do all that work, and you can hit pause and try it on your own, if you do all that work, you're going to end up with 10/3. Okay? It's not particularly difficult. Look, so real quick, what do we have? We have what? 2x squared, because when you bring up squared, divide by 2, the 4 becomes a 2. Minus x cubed over 3. That's going to go from 0 to 1. And then the green region, we have 4x minus x cubed over 3. And that's going to go from 1 to 2. You got to plug everything in. And yeah, that's where you're going to get your 10/3 from. You're going to have to deal with some fractions, and there's a lot of arithmetic to do there. But it can be done. What I want to show you is something a little more efficient. Okay? So let me erase the region inside for a second. Oops, I erased, unfortunately, my x squared as well. put my x squared back in there. There it is. Okay? So notice, if you draw those rectangles vertically, right? When you draw your vertical Riemann sums, you are differentiating with respect to x, always. But what if we turn it on its side? And instead of drawing vertical, we draw our horizontal. And we draw rectangles that would look like this, right? Well, you'll notice if you look at it horizontally, you're still doing Riemann sums, but you're no longer differentiating with respect to x. What you would happen now is you can differentiate with respect to y. And when you differentiate with respect to y, your Riemann sum rectangles must be now perpendicular to the y-axis. Okay? But what does that allow us to do? In the same way with the x-axis, you always take the upper function minus the lower function. When you're differentiating with respect to y, you need to go from the rightmost function minus the leftmost function. Well, that's this function, your y equals x squared, right, minus y equals 4x. The problem is, because we're differentiating with respect to y, our equations need to have y's in them. So, y equals x squared now needs to be solved for x. Well, that's the same as x equals square root of y. And y equals 4x is x equals y divided by 4. So now I have square root of y minus y divided by 4. And now we're going to look at the y-axis to see our lower and upper limits, or our a and our b. Well, we're going from 0, right, to, oh, well, that was easy, y equals 4, from 0 to 4. This one integral with respect to y should give us the same area as these two integrals differentiating with respect to x for the two separate regions. So let's try it. I'm going to erase what we have here. I don't want to erase it. I'll just scoop down. Let me rewrite my integral. 0 to 4. I'm going to write square root of y as y to the 1/2 minus y over 4 dy. And let's integrate. Integrate the same way you integrate with x. Same idea. So y to the 1/2 is actually y to the 3/2 divided by 3/2 is multiplication of 2/3. Y squared divided by 2 gives me y squared over 8. And now I'm going to go from 0 to 4. Plug in my values. So I have 2/3. 4 to the 3/2 minus 4 squared, 16 over 8, right? Plug in 0. Oh, that's just going to be 0 minus 0, right? So we have 2/3. All right, square root of 4. Let's do square root of 4 first. That's just 2. 2 cubed times 8. Minus 16 over 8 is 2, and that's 0. So I get 16/3 minus 2. Well, I'm going to put that over 3. So I'm going to multiply by 3 over 3. 6/3, 16/3 minus 6/3, 10/3. The same that I got up here. But done with one single integral as opposed to two in two different regions. So ultimately, your formulas for finding the area between two curves can be done with respect to x or with respect to y. And sometimes you have to look at the picture, sometimes it depends on how it's given to you, but a couple things to keep in mind. When it's done with respect to x, oh, sorry, scrolling around too much, notice the equations are solved for y. See, 4x minus x squared. When it's done with respect to y, the equations have to be solved for x, so the y's are put in there. So y, square root of y minus y over 4. So for area between two curves, or area doesn't even have to be between two curves. Clearly in that third one, we had a third boundary. Couple things. Suppose f and g are continuous functions. This will not work if they're not continuous functions. With f of x greater than g of x on a b, then the area is equal to a to b f of x minus g of x dx. For, again, f and g are continuous functions with f of y greater than or equal to g of y on, we'll call it a different interval, CD. Then your area is from C to D, f of y minus f of g dy. So again, sometimes you'll be told, sometimes you will just look at it and ask to find the area between, and you have to examine the picture. For example, if you had let's do right, y equals x squared minus 2, which is a parabola down here, right? And then the line y equals x. And you are asked to find this region, okay? Then you have to make a decision. Clearly, and again, think of those Riemann sum rectangles. To do rectangles, sorry, I keep getting rid of my function when I do that. To do rectangles and differentiate with respect to x, you can see here how you will have to do two different, you would actually need to do two different integrals. Okay. You'd have to do one here and then one on that side. All right. So to do those two different integrals, you need to find out where they intersect. So you need to find out where they intersect, and of course you can just do that by doing x squared minus 2 equals x squared minus x minus 2 equals 0, x minus 2, x plus 1. So that is the point -1, comma, since it's x equals y, it's -1. All right? So, to differentiate with respect to x, we also need this point. So this is the point where x squared minus 2 equals 0, x squared equals 2, x equals negative square root of 2. All right, that is the point negative square root of 2. So we would actually need to go from so to get the area in blue, sorry, you're going to go between negative square root of 2 and -1, and you're going to find the area of x squared minus 2. The other boundary is the x-axis, so you don't have to do that. It's just x squared minus 2. But because we're actually looking at area, you're technically looking at the area between the x-axis, which is 0, minus x squared minus 2. So you can find this area and take the absolute value, or you can think of it as 0 minus x squared minus 2. It kind of comes out to the same thing, which is then the integral from negative radical 2 to -1 of 2 minus x squared dx. But then you also have to add that to the area from -1 to 0 of 0 minus x. And you would have to add these two areas together. Now, if you did it with respect to y, then you are going completely from -1 to 0, because you're looking at the y values, right? This is -1, that's 0. And now you're going to do the rightmost function, which is, you got to rearrange it to y equals x equals y, so it's y minus, but then we got to change this, right? So instead of y equals x squared minus 2, you need y plus 2 equals x squared, and x equals the square root of y plus 2. It's the negative side of it. So minus negative square root y plus 2 dy, which kind of goes to -1 to 0. And you can integrate both of these. So the idea is that this integral should be the same as that integral. And I will leave you to integrate each of them the area does come out to approximately 0.7189, or if you do with respect to x and leave it in terms of square root, it looks like this. Okay, so that's how we do region between curves.